Alright, so we have talked about atoms, we have talked about their structure, how they're formed into elements, what the elements are, how they interact with each other to form molecules. We've looked at ionic bonds and then we've looked at covalent bonds. We recognise that covalent or sharing of the outer shell electron can break down into two forms. One, an equal sharing, which gives you no overall charge, and that is your non-polar covalent bonds. And the other one, which usually involves oxygen as one of the partners in the bonding, which is polar because the oxygen pulls the electrons away from the other atom, which is sharing its outer electrons. So now we can talk about the properties of water. At the end of the last talk, we discovered that water carries a partial charge to it because of the presence of the oxygen sharing its electrons with the two hydrogens. So the electrons of the hydrogens are pulled toward the oxygen molecule, and I'm showing that here. So here's our oxygen. Here's our oxygen's electrons it's sharing close to the oxygen, and the hydrogen electrons are pulled away from the hydrogen for the majority of the time. Sometimes both these electrons are down here and down here, keeping the hydrogen stable, but a lot of the time they're spent more toward the oxygen. Because it's not a complete donation of electron by the hydrogen, this takes on a negative charge from the hydrogen, but it's not a full charge, so we put this little squiggly thing in front of it or put brackets around it to show that it's a partial charge. We have two of them because we've got two hydrogen ions here, so two partially negative charges on the oxygen and then one partial positive charge on each of the hydrogens. So this EE, which is the here and here between the hydrogen and the oxygen, between them is a polar covalent bond, and this bond occurs within the water molecule between the hydrogen and the oxygen. The way it's structured and the way it pulled, there is a 120 degree. Whoops, I've written that wrong. I was going to do something else. That's correct. I'm having a good day today. So 120 degree bond angle. That becomes important when we look at cell membrane transport, because although water carries a charge, it can still go through a cell membrane, even though the cell membrane is mostly fat, because it can literally boomerang through it because of its angle. So it's very narrow on one side, so it can actually push through, and we'll explain that at the time. So we want to talk about the properties of water here, and water is the universal solvent. The only requirement for life that we are aware of is required is the presence of liquid water. So when we're talking about looking at the moons around Jupiter or even Neptune or whichever planet we happen to be talking about, the interest is really, is there liquid water somewhere on that moon or potentially a planet as we continue to explore the systems? And if there is, then there's a chance that life has occurred there. But if there is no liquid water, then we don't believe that life can exist, because so much dissolves in water. But why do they dissolve in water? Well, I've drawn a very bad glass of water here, and I've actually tried to draw the water molecules sitting in the glass. Now, I could have spent more time and filled this all up with water molecules, but then you wouldn't be able to really see the individual molecules. So what I'm trying to point out here is that here's an individual water molecule. I'm just going to draw that around it. Now look at this individual water molecule. So they're separate from each other, but then I've drawn these green dashes between the water molecules. So there's water molecule 1, here's water molecule 2, here's water molecule 3. So why have I drawn green dashes between them? Well, remind yourself that there is a partial negative charge on this oxygen because it's taking the electrons off here, and there is a partial negative charge here. This one's not currently being used, and then we've got a partial negative here, here, and then we have positive charges. We've done that one wrong. Alright. So I'm trying to illustrate a point here. Because of these things here, one water molecule, when it comes close to another water molecule, can interact with it because they're both charged. So this one, the oxygen, is interacting with this hydrogen here and this hydrogen here, which would be number 4. These very, 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 very weak bonds, because it's a bond, it's a really weak magnetic attraction between the negative on the oxygen and the positive on the hydrogen of another water molecule. So if this is the, here's the oxygen, here's the hydrogen, it's a very, very, very weak bond, easily broken. But when the water settles back down, it will then kind of orientate itself back toward the positive toward the negative. So these water molecules associate in a way that creates the presence of a new bond type. And the bond type is called a hydrogen bond, because it's between the partially positive hydrogens and, in this case, the negative of the oxygen, but the hydrogens will interact with other things and do the same thing. And because there's 2 hydrogens, it can interact with more and create lattice structures and things like that where there's only 1 oxygen. So the bond name is given to the hydrogen. Water molecules are kind of bonding with each other all the time in this way. In a liquid glass of water, they are actually attached to each other. Now the importance there, and this is why I've drawn this the way I've drawn it, is you've all probably had the experience of trying to carry, let's just say it's a beer glass, because I'm Scottish and I like beer. So you've got your beer glass and you've got your liquid. So this is like liquid over the top of your beer glass. So it's completely full, yet you can still pick it up and you can still carefully carry it over to your table, whatever, and then put it down again. And this is because in water, and beer is mostly water, in water you've got these bonds here holding the water molecules together. Even though it's gone over the lip of the glass, they're still holding, they're adhesing together because of these very weak hydrogen bonds. Now because they're weak, if you suddenly do that with the glass, it will slosh over because these bonds will break. But gently they can actually hold themselves together, which is kind of cool if you want to have a full, glass of beer instead of a 3/4 glass of beer. Not necessarily so important in biology. But what is important in biology are these hydrogen bonds in the water molecule for a number of reasons. One, because they exist, I think probably the most important is because they exist, they can interact with any charged molecule or ion or anything else. They can all come into water and dissolve. Hence we call water the universal solvent. Everything can just dissolve into it. That allows for lots of chemistry to take place in a water environment. So we are 67% water, because inside our cells, basically bags of water with chemistry taking place in them. Other solvents which do not have, or not capable of creating hydrogen bonds, etc., just aren't capable of doing as much chemistry. The other important thing about water is a very unusual property because of the hydrogen bonds. Generally speaking, if you've got a gas, you've got let's try and draw 3 volumes. So, in a gas, here's a box. You may have 4 molecules inside that space in a gas. Now in a liquid, much closer together. And in a solid, I could be here for a long time, so I'll just do a little bit. This is how, and that fills the whole thing, this is how close the atoms are to each other. So you see that they become closer and closer and closer when you go from gas through liquid to solid. Interestingly, water doesn't do that. Because you've got the gas here, fine, the liquid here, but when it goes to solid, because of, and I have to use a different colour, because of the hydrogen bonds, which I'm drawing in red here, between the water molecules, they hold them out, and these become rigid because the water molecules are now stuck in place. So whereas in the liquid these can break and they can slide past each other and pack in the solid you actually end up with the water expanding because of all of the hydrogen bonds get fixed in place. And if you don't believe me, just get yourself, a water bottle or something like that, a 500ml water bottle, and fill it up halfway, put the top on, put it in the freezer, come back in a couple of hours, and you'll see it's expanded. So water expands as a solid, it doesn't shrink. Why is that important? Well, it's extremely important for life. It's one of those things that here we have a basin of a lake and the water. Stick a boat on it. Little guy fishing. So here's our lake, guy fishing, large fish in the water. But when winter comes, the lake freezes. But because water expands and it freezes, only the top layer freezes, the rest of it remains liquid and allows life to exist even during the winter time, whereas other solvents, when they freeze all the way through. So the majority of life would be killed off. So again, another important property of water. But the key one to take home from this talk, hydrogen bonds. They can interact with charged molecules, form structures with them, but the bonds are extremely weak, so they can be rearranged very easily. But in proteins, for example, a lot of where they're switching on and switching off is all based on their shape, and the hydrogen bonds at the second level of structure in a protein can be easily altered. So you can make the protein active by holding one shape, but then switch it off by changing the hydrogen bonds. Easily to do, just bring some charge in close to it and these will all rearrange around it. Protein changes shape. You've now changed your function. So very simple information, but has a huge impact on physiology, particularly in the human. So thanks for listening.